Okay, so we need to talk about study outcomes, how the study turns out, whether we reject or fail to reject the null, and how that's associated with power. And in order to do that, we're going to have to talk about type 1 and type 2 errors, what kind of errors we can make. And I'll define all these terms. When the two population means are exactly equal, and remember that we have an assumption that sigma, the population standard deviation, is the same for all groups. So when mu1 is equal to mu2, then the distributions pile right on top of each other. So this red distribution of means and this green distribution of sample means, both these sampling distributions of the mean are right on top of one another when the null hypothesis is true, when the two means are exactly equal. When the null hypothesis is false and the two means are not equal, then the red distribution of sample means and the green distribution of sample means separate from one another. One mu, or mu1, is lesser in this case than mu2. So the means are not right on top of one another, and now we can see a separation of the sample means. And every time we do a study, every time we test the null, we have two possible outcomes. It might be that we reject the null, and it might be that we fail to reject the null. Well, if the null hypothesis is true and mu1 is equal to mu2, we don't want to reject the null because we would be rejecting a true null. We'd be rejecting the truth that the null is true. We do want to, however, fail to reject a true null. If the null hypothesis is false, we want to reject the null. When we reject the null and the null is true, we've made a mistake. When we fail to reject the null and the null is false, we've also made a mistake. So there are two ways to make a mistake for every testing of the null hypothesis, and two ways to get it correct. When we make a mistake by rejecting a true null, we call that an error, a type 1 error. When we make a mistake by failing to reject a false null, we call that a type 2 error. The probability of a type 1 error is called alpha. Alpha is also the size of the critical region. The probability of a type 2 error is called beta. And the opposite of beta, when we reject a false null and we make a correct decision by rejecting the null because the null is false, we call that power. Power is equal to 1 minus beta. When the null hypothesis is true, alpha is the size of the critical region, the probability of rejecting a true null. So both these mu's are the same, but if we get a sample mean from one of the group that's outside in the area beyond, in the critical region, we'll reject the null. And incorrectly so, we'll make an error, a mistake, a type 1 error. Alpha is the size of the critical region and also the probability of making that type 1 error. The experimenter determines the size of the critical region. We can pick from alpha 0.05, which most people use most of the time, or alpha 0.01. But it's up to us as the researcher. When the null hypothesis is false, there are lots of ways to make a mistake and lots of things that determine how much power we have, how much ability we have, what's the probability of rejecting that false null. And that's what we need to talk about. We want power. We want to be able to reject the null when the null hypothesis is false. So we're going to talk about who or what controls power. Remember that in every study, usually we want to reject the null, and larger z or t values are better. So a z-test, the formula is the sample mean minus mu over the standard error, and the standard error is sigma over the square root of n. So we know if we want large z-test values that all of those variables have something to do with that. So larger mean differences, We have larger z-test values, a smaller sigma. We have larger z-test values, a larger n. We have larger z-test values. So power is about the separation of the red means and the green means, how separated they are. The more separated they are, the more likely we're going to get a green mean that is different from mu1, or a green mean that we can tell apart from a red mean. The more the groups look different, the more the distributions are separate, the more power we have. So here's a case where almost all the green means look just like and occur in the same space as the red means. So we have low power right here. The difference between mu1 and mu2 is really small. So those distributions overlap really a lot. And we have not a lot of power to detect real differences, the real difference between mu1 and mu2 that exists. Now the two distributions have separated from one another. The distance between mu1 and mu2 is larger, and we have more power. More than half of those green means are in the critical region, which means that if we get any of those green means that are in the critical region, we're going to reject the null, and rightly so. Sigma is a determinant of power. Large sigma values mean large variations in the scores. If the scores are spread out a lot, then the means are spread out a lot. And if the means are spread out a lot, then even if the mean differences are fairly large, the distributions will overlap quite a bit. So when sigma is large, the variability of the raw scores, we decrease power. Here we have a smaller standard deviation of raw scores, so sigma equals 1 compared to sigma equal 10 in the distributions before. That smaller variability of raw scores scrunches up those distributions so that they're slimmer and they're more distinct from one another. Even though mu1, the distance between mu1 and mu2 is exactly the same in the two distributions, we have more power with smaller values for sigma because the distributions are more compact and more distinguishable from one another. Because the sample size is the denominator in the standard error, the sample size, a small sample size, makes for a big standard error, and a big standard error is big variability between means in the sampling distribution of the mean. So here we have a small sample size and not a lot of variability in the means that's not overlapping between one distribution and the other. So small sample size, less power. Here we have the same distance between the means, so mu1 minus mu2 is exactly the same, but now we have an n of 1,000, and what that n of 1,000 does is it makes the standard error a lot smaller because that's the denominator of the standard error. And when the standard error is small, the distribution is scrunched up, it's slimmer, more distinction between those distributions, and more power. Alpha of 0.05, this is the reason most people use 0.05 most of the time, because alpha of 0.05 gives us more area, 5%, in the critical region compared to 0.01, which would only give us 1%. So more power as alpha increases. And a one-tailed test has more power because we put all of alpha in the tail that is most likely to have the difference. So if we place that tail appropriately and use a one-tailed test, we have more power, 5% all in one tail to detect mean differences instead of 0.025 or 2.5%.